Hello everyone. So we are continuing with the previous lecture. We ended with the linearization theorem, which states that given that lambda 1 and mu are eigenvalues of the Jacobian matrix from the linearized system, if the real part of lambda is not 0, the real part of mu is not 0, and they are not equal, so you don't have repeated eigenvalues, then the qualitative behavior of solutions of the nonlinear system near the equilibrium point is the same as the behavior of the linear system near the equilibrium point 0, 0. Remember that in the planar linear systems, we said 0, 0 is always a fixed point or an equilibrium point of the system. Okay, that's why this is there. But this was a linearization theorem, and we said that it basically covers cases where you have stable and unstable nodes, stable and unstable spiral points, as well as saddle or hyperbolic points. The theorem does not include cases where you have purely imaginary eigenvalues like centers, or improper nodes where you have repeated eigenvalues. Okay? So in these two cases, we can't really say much about the behavior of the nonlinear system around the equilibrium point. And so this is where when we get into Lyapunov functions, then you could use Lyapunov functions to help you analyze these ones. Okay? So here's an example. We want to find the equilibrium points and their nature for this nonlinear system. This is nonlinear basically because of this term, this x times y. That makes it nonlinear. And hence we want to plot a possible phase diagram of the system. So the phase diagram will basically be phase diagrams around the equilibrium points. Okay, remember we don't know much about what is happening in the whole plane. So the approach is straightforward. What you do is find the equilibrium point by setting the right hand side of each of the equations to 0 and solving for x and y. That will give you the fixed point. So for this case you have this. From the first equation you have this is 0, which implies y is 0 or x is negative 2, right? And from the second equation y is equal to negative x. So if y is 0, from the second equation x is also 0. And if x is negative 2, y will be positive 2. And so you see that 0, 0 and then negative 2 becomes the two equilibrium points for the system. Once you have your equilibrium points, then you go ahead to compute your Jacobian matrix. All right? It is given by this, right? The f1, the x, the f2, the y, and this term. If you do that, right, f1 here is basically this guy here, the first equation. F2 is the second one. So differentiate this with respect to x, and that will just give you a y. If we differentiate with respect to y, you get a 2 plus x. Differentiate the second one with respect to x, you get 1. With respect to y, you get a 1. So this is a Jacobian. So you analyze, look for the Jacobian matrix at each of the equilibrium points. So for 0, 0, you plug in, wherever I see x, I put 0. Where I see y, I put 0. And you do the same for here. Wherever you see x, you plug in negative 2. Where you see y, you put 2. And that will give you the matrices, and then you analyze the matrices for the behavior of the equilibrium points. So case 1 is for the equilibrium point 0, 0. So the Jacobian matrix at 0, 0 will be given by this, right? You plug in the zeros and you get this system. Find the eigenvalues of this. If you do, we know how to do this, right, from the previous lectures. Lambda 1 is negative 2, lambda 2 is 2, and with this corresponding eigenvectors. So you have distinct eigenvalues, one negative, the other positive, all right? Which means that the equilibrium point of fixed point 0, 0 is a saddle for the linear system, okay? But the linearization theorem guarantees that since it is a saddle, right, since the eigenvalues are distinct, you can conclude that the nonlinear system will also have a saddle around this equilibrium point. Okay, so that is how important the linearization theorem is. Okay, so that gives us this. Then you go on to the second case, the case where the equilibrium point, we have a second equilibrium point, negative 2, 2. You can compute the Jacobian matrix for that, and that gives you 2, 0, 1, 1, right? And then find the eigenvalues and eigenvectors. Eigenvalues are 1 and 2, and corresponding eigenvectors are these. Okay? In fact, for the nature of the equilibrium points, you don't need the eigenvectors. You need the eigenvectors if you want to plot possible phase solutions. So from the eigenvalues, we see that we have purely positive eigenvalues. They are distinct. So these are unstable node. All right? The unstable node is covered by the linearization theorem. Okay? So since the fixed point negative 2, 2 is an unstable node, but from the linearized system, by the linearization theorem, we can also conclude, right? We can also conclude that the nonlinear system will have an unstable node at this equilibrium point, negative 2, 2. Okay? So there is this correspondence between them. If, for instance, we had repeated eigenvalues, then we can't really make any conclusion based on the linearization theorem. But because it is an unstable node, right, which is included in the theorem, then we can make this conclusion. All right? So how do you plot a phase diagram? So you can plot a phase diagram for each of the equilibrium points. So at a fixed point 0, 0, we know the eigenvalues and we know the eigenvectors, so we have a solution for it, right? Which is given by this. So you can split this into, the x and the y components of the solution. You can do the same thing for the fixed point negative 2, 2, and you have the solutions x is this and y is equal to that. Okay, this is straightforward. And so I used GeoGebra to plot it because I want it to look nice and put in my lecture. But you can plot the phase diagram by hand, right? If you use curve, which is used in plotting parametric equations, then you can actually plot these and these ones, okay, in the same figure. So to do that, what I did was write the x to be equal to this minus 2. This minus 2 is like x1 star, and this one is like xi1 from our original development, right? And then these two terms are like my xi2, and this is plus 2 here is like x2 star, all right, equilibrium points. And so if I write it this way and plot it, I will have a phase diagram that is centered around negative 2, 2. So you can plot this and plot that, and then this is what you get. Okay, you get this nice figure. So if you do the first one, we had a saddle. So at 0, 0, we saw that it was a saddle, which means that if we had a solution for the whole nonlinear system, we'll see that at 0, 0, the system is behaving as a saddle. Things are moving in this form. And then the other equilibrium point is at negative 2, 2, all right? If you plot it, you see that this is how the system behaves. And so this is also saying that if we had a solution for the whole nonlinear system, and you look or you zoom in at negative 2, 2, what you'll find is that you'll find trajectories are behaving like this around this equilibrium point. So basically this is the linearization, what the linearization approach does. It gives you solutions, or it tells you the qualitative behavior of solutions around the fixed points. In this case, negative 2, 2 and 0, 0. So I can't really say much when I move far away from these fixed points, all right? All I can say is, what is happening around the fixed points, all right? So I have some nice exercises here. I will choose, a few of them for you to try and submit them. I'll decide which ones maybe see in these ones. But you can follow the similar approach as I have done for this case, and then you can sketch your possible phase diagrams. And then here you are not sketching it, you are just finding the fixed points, okay, the linearization. In other words, you want find a linear system, this nonlinear systems. Okay, so our next lecture will be on, I think, the Lyapunov functions. So I'll let you know when I do that. All right, all the best.